Silver is a better conductor of electricity than gold. The conductivity of a metal is a measure of its ability to conduct an electric current. It's typically measured in units of Siemens per meter. The higher the conductivity, the better the metal is at conducting electricity. The conductivity of silver is 63.0 times 10 to the 6 Siemens per meter, while the conductivity of gold is 45.2 times 10 to the 6 Siemens per meter. This means that silver is about 1.4 times better at conducting electricity than gold. The high conductivity of silver makes it a valuable metal for use in electrical applications. It is often used in electrical contacts, wires, and other components where good conductivity is essential. To understand electrical conductivity, it's helpful to consider the movement of electrons within a material. Metals, including silver and gold, have a sea of electrons that are free to move throughout their structure. These free electrons are what allow metals to conduct electricity. When an electric field is applied across a metal, these free electrons are accelerated, creating an electric current. The ease with which these electrons can move determines the conductivity of the metal. Several factors influence a metal's conductivity. Firstly, the number of free electrons per atom plays a significant role. Metals with more free electrons generally exhibit higher conductivity. Secondly, the mobility of these electrons is crucial. Mobility refers to how easily electrons can move through the material without being scattered or impeded. Factors that can hinder electron mobility include impurities, defects in the crystal structure, and temperature. Impurities and defects act as scattering centers, disrupting the flow of electrons and reducing conductivity. Higher temperatures increase atomic vibrations, which also scatter electrons and decrease conductivity. Silver possesses a high number of free electrons and relatively low electron scattering, resulting in its superior conductivity compared to gold. While gold also has a good number of free electrons, its electron mobility is lower than silver's. This difference in electron mobility accounts for the difference in conductivity between the two metals. The practical implications of silver's high conductivity are significant. In electrical applications, using silver can reduce energy loss due to resistance. This is particularly important in applications where minimizing energy waste is crucial, such as in power transmission and distribution. Silver is also used in high-frequency applications, such as in radio frequency connectors and waveguides, where its low resistance minimizes signal attenuation. However, silver is more expensive than gold, which limits its use in some applications. Gold is often used as a plating material on electrical contacts and connectors because it is resistant to corrosion. Corrosion can increase the resistance of a contact, leading to signal loss or failure. Gold's corrosion resistance ensures a reliable connection over time. In some applications, a combination of silver and gold is used to take advantage of the benefits of both metals. For example, a connector might be made of a base metal with a silver plating to provide good conductivity, and then a thin layer of gold on top of the silver to protect it from corrosion. Other metals, such as copper and aluminum, are also commonly used in electrical applications. Copper is a good conductor of electricity and is less expensive than silver. Aluminum is lightweight and is often used in overhead power lines. The choice of metal for a particular application depends on a variety of factors, including conductivity, cost, corrosion resistance, weight, and mechanical strength. In summary, silver is a better conductor of electricity than gold due to its high number of free electrons and lower electron scattering. This makes silver a valuable metal for use in electrical applications where high conductivity is essential. However, the higher cost of silver may limit its use in some applications, and other metals such as copper and aluminum may be used instead, depending on the specific requirements of the application. Conductivity is a fundamental property of materials that affects their ability to conduct electric current. It is essential to select the appropriate materials for electrical applications to ensure optimal performance and reliability. The measurement of conductivity is typically done using a 4-point probe method. This method involves passing a current through the material and measuring the voltage drop across a known distance. The conductivity can then be calculated using Ohm's law. Conductivity is also temperature dependent. As temperature increases, the conductivity of most metals decreases. This is because high temperatures increase atomic vibrations, which scatter electrons and reduce their mobility. There are some materials, such as semiconductors, that exhibit an increase in conductivity with increasing temperature over a certain range. This is because higher temperatures can excite more electrons into the conduction band, increasing the number of free electrons available to carry current. Superconductors are materials that exhibit zero electrical resistance below a critical temperature. This means that current can flow through a superconductor without any energy loss. Superconductivity is a quantum mechanical phenomenon that occurs due to the formation of Cooper pairs, which are pairs of electrons that are bound together. These Cooper pairs can move through the material without being scattered, resulting in zero resistance. Superconductors have a wide range of potential applications, including high-speed computing, magnetic levitation, and lossless power transmission. However, most superconductors require extremely low temperatures to operate, which limits their practical use. Research is ongoing to develop superconductors that can operate at higher temperatures. In addition to metals, other materials can also conduct electricity. Electrolytes are solutions that contain ions, which are charged particles that can carry current. Electrolytes are used in batteries, fuel cells, and other electrochemical devices. Semiconductors are materials that have a conductivity between that of a metal and an insulator. The conductivity of a semiconductor can be controlled by adding impurities, a process called doping. Semiconductors are used in transistors, diodes, and other electronic components. Insulators are materials that do not conduct electricity. Insulators are used to prevent electric current from flowing where it is not wanted. Examples of insulators include rubber, plastic, and glass. The choice of material for a particular electrical application depends on the desired conductivity, as well as other factors such as cost, mechanical strength, and temperature resistance. Understanding the properties of different materials is essential for designing and building electrical systems that are safe, reliable, and efficient. The study of conductivity and other electrical properties of materials is a fundamental aspect of electrical engineering and materials science. This knowledge is used to develop new materials and devices with improved performance and functionality. As technology advances, the demand for materials with specific electrical properties continues to grow. This drives ongoing research and development in the field of materials science, leading to new discoveries and innovations that benefit society. Electrical conductivity is a key parameter in many engineering applications, ranging from power generation and transmission to electronics and telecommunications. A thorough understanding of the principles of electrical conductivity and the properties of different materials is essential for engineers working in these fields.